This is the last part of section 1.2, and the difference between the first part and the last part is the last parts want me to find limits at infinities, and limits at infinities we can get by algebra, we can get by tables, we can get by graphing. Let me do the table, and then I'm going to sketch a graph, and then I'm going to do the algebra. So this is not very pleasant, but to find a limit using a table, I need to know decent numbers to plug in. And so I want to find the limit as x goes to positive infinity. So I made my table with numbers that went from smaller to larger. It's a one-sided limit. And they got close, not terribly close to infinity, but they got pretty darn big as I care to enter on my calculator. So to get a guesstimate of what the limit is, I'm going to go 6. I'm going to just plug in for each of these values of x, the value in the table that's for x. So for this y value, I'm going to do that. Bring my calculator down. So I'm going to go on, clear. I need the whole numerator in a parenthesis, so I have to go, let me just do the numerator separately. I'm going to go 6 times parentheses 100 squared plus 2 times 100 plus 5. So the numerator comes out to 60,205. And I'll do the denominator now, which is 3 times 100 squared plus 4 times 100 minus 4, which is 30,396. Now I'm going to divide those two. So I'm going to go 60,205 divided by 30,396. And that's 1.98. So the first number I'm going to plug in my table is 1.98. And I'm going to do the same thing for 1,000. I'm going to go 6 times 1,000 squared plus 2 times 1,000 plus 5 over 3 times 1,000 squared plus 4 times 1,000 minus 4. If I want to enter that all at once, rather than doing the two separate numbers like I did for the first value, I can do it, but it's messy. To do it all at once, you'd have to do this. Clear parentheses for the 6 in front of the 6, then I'd go 6 times 100 squared plus 2 times 100 plus 5. Close out of parentheses, so basically I added a parentheses here and here. I'm going to add a parentheses there and there. I'm going to put a divide sign to separate the numerator from the denominator, and then parentheses 3 times 1. I'm supposed to be doing 1,000, aren't I? Let me go back here. Second, insert 0. Second, insert 0. So there's the numerator fixed. And now the denominator is 3 times 1,000 squared plus 4 times 1,000 minus 4. And I get 1.998. I'm going to do the same thing, but I'm going to change the 1,000 to 100,000. So I'm going to go parentheses 6 parentheses 100,000 squared plus 2 parentheses 100,000, which is 5 zeros, parentheses plus 5 parentheses divided by, and then parentheses in front of the 3, and then 100,000 squared, plus 4 times 100,000 minus 4, close the parentheses, and I get 1.99949s and an 8. That's enough for me, but I'll do the million just because it's there. So parentheses 6 parentheses a million, 6 zeros, 1, 2, 3, 4, 5, 6 squared plus 2, and then 1, 2, 3, 4, 5, 6 zeros plus 5, close my parentheses, divided by parentheses 3, parentheses 1, and then 6 zeros, parentheses squared, plus 4, parentheses 1, 6 zeros, minus 4, parentheses, and I get 1.999998. Okay, so if I had to guess what the limit is, I didn't get very close to it. I didn't get very close to infinity because a million is not quite infinity, a trillion is not quite infinity. But my guess is my answer to 22a is that the limit is 2. All right, so now I'm going to use my calculator to confirm. And anytime I use my calculator, I need to have a good window. And my x's need to get close to infinity. And so maybe for my x min, I don't know, I'll start at 0, but that's not terribly close to infinity. I'll make my x max maybe this a million. Maybe I'll make it 10 million, which is kind of close to infinity. Well, not really, but it's big anyways. And then my limit's 2, so I'm going to make my y min 1 and my y max 3. And having that window, I should be able to use the trace function. I'll trace all the way out to the far right edge of the graph, and I'll get numbers that are getting closer and closer to 2. I'll get these kinds of numbers, or let me see exactly what I get. So I'm going to enter this on my y equals. So I'm going to go y equals clear. All right, so the screen probably looks different. When I was entering this function to check the limit at infinity by graphing, I entered the denominator wrong, and I actually entered the last 2 terms in the denominator wrong. It turns out that if I only enter the first term in the numerator and the first term in the denominator correctly, then the limit at infinity is going to be correct even if I mess up the last few terms. But I'm redoing, and I'm going to cut it and paste, so it's going to be a little bit of a, I don't know, start and stop in my video. But I just talked about the window that I want to set, and I want to graph the function, and I'm going to trace all the way out to the right edge of the graph. The y coordinate, what I expect to find is 2, because when I did part A, the limit as x went to infinity of the function 6x squared plus 2x plus 5 over 3x squared plus 4x minus 4 equals to 2. And this graphical checking is really just for you. So if you're doing a problem on a test, you can graph to make sure your limit is right. On the test, I won't ask you to sketch a graph and confirm. You kind of notice when I'm doing the part B's, I'm not really writing anything down other than maybe the window that I used, and I'm just confirming my answer. And so this is not really test worthy, the part B's, but they're definitely worth doing. So when I go to do part B of 22, I'm going to enter the function. So y equals, and then clear parentheses, the numerator goes in the first parentheses, so 6x squared plus 2x plus 5, close my parentheses, put a divide sign, and then parentheses for the denominator, 3x squared plus 4x minus 4. If I didn't adjust my window properly, I might not see the limit that I need to see. So I'm going to hit my window button, change the x min to 0, the x max to 10 million that we discussed, and any large numbers, that's, I don't know if that's 10 million, so 1, 0, 1, 2, 3, 1, 2, 3. 1 million would be sufficient, 100 million might be sufficient. When you're trying to find a limit at infinity, you know, any value of x, probably even over 1,000, would be adequate to see the limit that you need to see. I just want to make my y's 1 and 3. The reason the y's were 1 and 3 is because I knew ahead of time the limit was 2. So if I make my y min less than the limit at infinity and the y max greater than the limit at infinity, then I know I'm going to see on my graph the limit. The graph itself isn't going to show a lot of detail. probably won't see any maximums or minimums, but that's not important. When I'm trying to find a limit at infinity, I'm only worried about the far right edge of the graph, and I'm going to see that when I hit my graph button. And the graph is actually going to probably look like a straight line, which is a good thing. That's kind of what I expect to happen. When a limit exists, and if I set my, at infinity, if I set my window to a really extreme wide window, then the graph is probably just going to be a horizontal line. So to find this limit, I'm going to hit second, I'm just going to hit the trace key without the second, and then I'm going to start tracing. And as I start tracing, I'm not really paying attention to the x's, I'm paying attention to the y's. And I would love to see y equal to 2 as I trace further and further to the right. You'll notice right now I'm at y equals 1 and then 6 9s and a 6. If I trace that a little further to the right, I get y equals 1.69 and a 7. And if I even go a little bit further, the x's are getting bigger and bigger. Here my x is at 7,659,000. The y's are 1.69 and a 7. And eventually, the further I get out, the closer my y is going to be to 2. It's never going to get to 2. If I went further and further on my x-axis, or on this trace, I think I could get the y's to be a 1 point and then a string of 7 9s, but I'll never get it to be 2. This is because the graph is always slightly below the horizontal line of y equal to 2, and the y-coordinate will never be 2. It will get as close to 2 as possible, meaning as many decimals as my calculator carries accuracy, I can get a 1 in that many 9s in my calculator y display, and that is good enough for me to believe that my limit is 2. The graph is clearly flattening out, and when the graph flattens out, you know that the limit to at infinity exists, and it's whatever y this is approaching. So hopefully that was adequate. I must clip this in, and then you're going to see probably another break in the video as I cut this out. Alright, so I just finished 22b. I didn't make a smooth transition into 22c, and that's about what you're going to see next. For the next kind of screen that you'll see me working on is I'll be working on solving problem 22c, which is finding this limit at infinity using algebra. Now the algebra, which is the tricky part. So in order to find a limit at infinity, I can't plug infinity in. Plugging infinity in isn't going to help a bit. And what I'm going to have to do to find a limit at infinity is look at the problem and find the highest exponent that occurs for the x. And in this case, the highest exponent is x squared. What I'm going to do is I'm going to multiply the numerator and the denominator by 1 over the highest power of x that occurs. And in this problem, the highest power of x that occurs is x squared. So I'm going to multiply the numerator and the denominator by 1 over x squared. And I'm going to distribute this through the fraction. So I can rewrite this problem as the limit as x goes to infinity of 6x squared times 1 over x squared plus 2x, I didn't put a fraction there, times 1 over x squared plus 5 times 1 over x squared. And then in the denominator, I'm going to go 3x squared times 1 over x squared plus 4x times 1 over x squared minus 4 times 1 over x squared. So I distributed the 1 over x squared, which is 1 over the highest power of x that occurs in either the numerator or the denominator. I distributed it through the fraction, and now I'm going to cancel. In the first canceling, the x squareds are going to cancel. There's no fraction left. The limit still remains. But I'm left with there is just the number 6 times 1, which is 6. For the next canceling, I'm going to cancel this x with one of the 2x squareds. There were 2 x's down here. When I cancel one of them, there's still one left. So I'm left with 2 times 1 over x. I'm going to multiply the 2 times 1, and I'm going to leave the x in the denominator, and I'm going to make this 2 over x. There's no canceling for the next one, so I'm just going to multiply the 5 and the 1 and get plus 5 over x squared. In the denominator, I'm going to cancel x squared with x squared. I'll be left with 3 times 1, which is 3. And then with this, I have 1x to cancel with one of the 2 x's. It'll leave me with no x next to the 4, but an x there in the denominator. I multiply the 4 times 1 and leave the x in the denominator and get 4 over x. And then the last piece, I just multiply the 4 and the 1 and get minus 4 over x squared. After you multiply every term by the 1 over the highest power of x that occurs in the numerator or the denominator, the only x's that occur are in the denominator. Now I can plug infinity in. I'm going to get 6 plus 2 over infinity plus 5 divided by infinity squared. And then I get 3 plus, that's horrible looking, 4 over infinity minus 4 over infinity squared. So that's what the limit would look like when I plug the infinity into the fractions. Any fraction that has an integer in the numerator and an infinity or an infinity to some power in the denominator is 0. Because if I took 2 and cut it into infinitely many parts, it'd essentially be microscopically small, and we call that 0. So each one of these fractions we're going to say is equal to 0. So it's going to be 6 plus 0 over 3 plus 0 minus 0, which is 6 over 3, which is the 2 that I got from my table. Which is the 2 that I got from my table. And that's the answer of how to find the limit algebraically. So you got the same kind of problem for 21 that you need to make a stab at now. So you should try to do 21 the best you can. Fill in the table to figure out what the limit is. And then based on your table and what the limit is, you'll make a window. Because we're going to infinity, usually I make my x min 0 and my x max something kind of large. And 1,000,000 or 10 million is definitely large enough. And then my y min and my y max are going to be dependent on what the answer to what you think the limit is. I think 1 and 3 are going to suit you just fine. And if you do that and you trace along, you'll see what the limit is. And then you're going to use the algebra trick that I showed. And you might not know the algebra trick yet, so I will revisit it a bunch of times in this section. Let me be lazy on 24 and use my calculator to get the y's. So the first thing I'm asked to do is find a bunch of y values. And I've been inefficient on getting my y values. Let me be more efficient. So how do I become efficient? I become efficient by taking the function I'm trying to find the limit of and plop it right into my y equals. So if I'm trying to find the limit as x goes to infinity of that horrible fraction, I'm going to just plug this into my y1. So I'm going to go 2x squared plus 2x minus 5 divided by parentheses 3x to the 4th minus 5x plus 2. I've entered the function in. I can hit graph if I want to. I don't know if I'll see anything because the limit might not be in my window, but that's okay. What I can do now is find the y values. So I'm going to go second calc, hit enter on value, and the first number I'm plugging in is 100. So I'm going to type in 100. And it tells me so my calculator came back with 6.7317 e to the negative 5. that tells me to move the decimal 5 places to the left. So I'm going to go 1, 2, 3, 4, 5. I'm going to move the decimal 5 places to the left, and any place there I had to move the decimal where there wasn't a number, I need to put a 0. So this is going to be decimal 1, 2, 3, 4 zeros, and then 6, 7, 1. That's enough. That's a pretty darn small number. It's pretty close to 0. It's positive, but it's a small number. Let me do 1,000. I'm going to go second, calc, value, type in 1,000, and it gives me 6.6733 e to the negative 7, which means I need to drag the decimal 1, 2, 3, 4, 5, 6, 7 places to the left. Means I'm going to have to add in 6 zeros, so it's going to be 1, 2, 3, 4, 5, 6 zeros, and then the 6733. Again, that's a small number, but it's bigger than 0. I'll do for 100,000. Second, calc, value, 10000, and I get 11 places where I need to move the decimal. So I got 6.667 e to the negative 11. I need to move the decimal 11 places, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, which means I have to have 10 zeros, so it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros, and then the 667. And now I'll do a million. Second, calc, value, a million. 1, 2, 3, 4, 5, 6 zeros. Have to move the decimal 13 places, which means I'm going to have 12 zeros and then those numbers. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 6, 6, 7. Well, that tells me what the limit is, because each one of these numbers is positive, but it's getting progressively smaller. It's getting progressively closer to 0. So I'm going to say the limit. So the answer to part A, the limit is going to be 0. And I actually have this graphed well enough. If the window that I chose, if I was graphing this, I'd probably do x min 0, x max, a million or 10 million. Let me just bop it down to a million. That's far enough. And then my y min, I might do negative 1, and my y max, I'd probably do 1, because if the limit is 0, I want 0 to be in my limit, in my window. So if I want to change my window, I have the function in there already. Let me just change this to a million. And then y min negative 1, y max 1. And when I hit graph, I don't see a darn thing, because the graph is so close to the x-axis that you can't distinguish the graph from the x-axis. It actually drew something. It probably drew it basically on top of the x-axis. Now when I hit my trace feature, and I start tracing out, it's actually tracing on the graph. It's not on the x-axis, it's just right above the x-axis. And you look at the y's, those y's are all essentially 0, because each one of these y's, I have to move the decimal to the left. So for this particular y, I'd get 12 zeros, a decimal, 12 zeros, and then 7783. That is what happens when a graph has a limit of 0. So my guess is that the algebra, the table, and the graph are saying the same thing, that the limit in fact is 0. Now I'm going to do algebra to find the limit, and when I do algebra to find a limit, I multiply by 1 over the highest power of x that occurs, and x to the 4th is the highest power of x that occurs. To save a little room, I'm just going to go straight to the more simplified steps. So I'm going to take each term and multiply it by 1 over x to the 4th. That's in effect what I do when I multiply the whole thing by 1 over x to the 4th times 1 over x to the 4th. So just like I did in the algebra phase of the last problem, I'm doing the same thing. X to the fourth was the highest power of x that occurred anywhere in the problem, so I multiplied the whole fraction by 1 over x to the fourth over 1 over x to the fourth, and in effect, what that has me do is multiply each term by 1 over x to the fourth. Now I'm going to cancel. Here, the x squareds are going to cancel, and that x to the fourth is going to turn into an x squared. And in the numerator, I'm going to be left with 2 times 1, which is 2, and then in the denominator I have that x squared. So the very first term, I'm going to write 2 in the numerator, x squared in the denominator. The second canceling, I'm going to cancel the x with the x to the fourth. This x is going to be gone. I canceled one of the 4 x's away, so I'm going to be left with an x cubed there. And when I do this multiplication, it's going to be 2 times 1, which is 2 in the numerator, and then x cubed in the denominator. Last one in the numerator, there's no canceling. I multiply the minus 5 times 1, and I get minus 5. And I leave the x to the fourth in the denominator. In the denominator, the first fraction goes away completely. The x to the fourth cancels out. And I multiply the 3 times the 1, and I get a 3. Second fraction, I cancel the x with the x to the fourth. I'll be left with an x cubed in the denominator. I multiply the 5 and the 1, and I get minus 5 over x cubed. And the last fraction, I multiply the 2 times the 1, and I get 2 over x to the fourth. Now I have just a boatload of fractions. I'm going to plug infinity in for the x's. So I'm going to get the limit. Whoops, I won't write the limit anymore because I'm plugging the infinity in. I'm going to get 2 over infinity squared plus 2 over infinity cubed minus 5 over infinity to the fourth over 3 minus 5 over infinity cubed. I don't know what these double plus signs are. And then plus 2 over infinity to the fourth. Any fraction that has an integer in the numerator and any power of infinity in the denominator is equal to 0. So this is going to be 0 plus 0 minus 0 in the numerator. And in the denominator, it's going to be 3 minus 0 plus 0. The fractions that have infinity in the denominators go to 0. This comes out to 0 over 3. And any fraction with 0 in the numerator is equal to 0. So the algebra confirms what my table and what my graphs are telling me, that the limit is 0. All right, we'll do a bunch of these. We got a couple more tables to do. So you should be able to have exactly the same skill as problem 24 that I just did. You may not be able to do problem 25 because it has a trick. I'm going to move on to do problem 26. 26, I'm going to do my table. And you notice my x values didn't get that big. They didn't get up to the millions. It's because in this particular problem, the y's are going to get out of control big. So I tempered my table a little bit. I'm going to get my y's to fill in the table slickly. So I'm going to go to my calculator. I'm going to enter my y equals, clear this out, and do 2x up arrow 7 plus 2x up arrow 3 minus 5, close out my parentheses, divided by parentheses 3x up arrow 4 minus 5x, close my parentheses. For my window, my x's need to go between 10 and 40. So I'm going to go, well, I'm going to make them go 0 to 40 then. And then my y's, I don't know what they should be. I'll make them 0 to 10. I know that's not good. But I don't, for completing the table, as long as I have my x's have the values that the table encompasses, it'll be okay. I'm not going to see much of a graph at all, but I don't care because my table will save me here. So first thing I'm going to do is now second calc value and plug in 10 for x And when I plug in 10 for x, I get 667.85 for y. I'll round to 2 decimals when it's comfortable. Next value, I plug in 20, so I go second, trace, value, type in 20, and I get 5,334.48. Just because I could write the 478, I just didn't feel like I had room to do it. And then second calc for the next value, 30, I get 18,001.133. And then the last one, second calc value 40, I get 42,667.79. I don't care if you round to 2 decimals or if you give me the whole value, if you can squeeze it in. So when I look at those y's aren't stabilizing. And when the y's keep getting bigger and bigger and bigger, we say the limit doesn't exist. Which means graphically, the graph is going to shoot up real high. In the last section when we did limits from a graph, what happened when the limits didn't exist is at infinity, the graph would just shoot up real high. Let me just hit zoom in standard to show you a reasonable picture of this graph. And so you can see that the limit doesn't exist. For the limit at infinity to exist, well, there's some asymptotes here. For a limit at infinity to exist, the graph has to flatten out. And this graph doesn't flatten out. Let me make the y's a little bit higher. Maybe make my y's go up to 100. And you'll see on the graph, when I get out to the far edge of the x-axis, the graph doesn't exist. It just keeps going up and up and up. And when a graph just keeps going up and up and up and up, that's graphically when a limit at infinity doesn't exist. Limits at infinity only exist if the graph flattens out as you go further down the x-axis. So my calculator says this limit does not exist. And I don't know why I didn't say use algebra to find the limit, but I should do it. Let me show you the algebra of what happens when a limit doesn't exist. So it's not on here, but I'll do this. I'm going to show the limit doesn't exist using algebra. It's going to be the same algebra strategy. So in this problem, x to the 7th is the highest power of x. So if I'm trying to find the limit at infinity of a fraction, I multiply every single term in the numerator and in the denominator by 1 over that highest exponent of x. So I'm going to multiply everything by 1 over x to the 7th, because x to the 7th is the highest power of x that occurs in this problem. So what's going to happen is in the first canceling, the fraction's going to go away, and I'm going to get 2 times 1, which is 2. So I'm going to get the limit as x goes to infinity. That piece is a 2. For the next one, I have an x cubed, and it's going to cancel out 3 of the 7 x's. I'm going to be left with an x to the 4th. And I'm going to multiply the 2 times the 1, and I'm going to get plus 2 over x to the 4th. In the last one, there's no canceling. I just multiply the 5 and the 1. I get minus 5 over x to the 7th. In the denominator, this x to the 4th and this x to the 7th cancel. I lose all 4 of these x's. I lose 4 of the x's from the 7 x's. I'm left with 3 x's. I multiply the 3 and the 1, and I get a 3 over x cubed. The last one, I'm going to wind up multiplying the 5 and the 1, and I'm going to cancel 1 of the 7 x's and be left with an x to the 6th in the denominator. So this is going to be minus 5 over x to the 6th. And now I'm going to plug my infinities in. When I plug my infinities in, I don't write the limit anymore, so this is going to be 2 plus 2 over infinity to the 4th minus 5 over infinity to the 7th over 3 over infinity cubed minus 5 over infinity to the 6th. The numerator is going to be 2 plus 0 minus 0, because any fraction with an infinity or a power of infinity in the denominator is equal to 0. And the denominator is going to be 0 minus 0. So this whole thing is going to come out to 2 over 0. And that's what happens when you have a limit at infinity that doesn't exist. You're left with a 0 in the denominator. So the algebra shows me that this doesn't exist. And it's a little bit different than the last algebra. The last algebra that I did when I went to find the limit and it was 0, the 0 was in the numerator. So when you're finding a limit at infinity, if you're left with a 0 in the numerator, the limit is 0. If you're left with a 0 in the denominator, the limit doesn't exist. And then the other thing that we had is just you had a nice lovely limit like a few problems ago where you just were left with a fraction that reduced. So when we're going to find a limit at infinity, if both the numerator and the denominator aren't 0, you just divide those numbers and that's what the limit is. If the denominator is 0, the limit doesn't exist. If the numerator is 0, the limit is 0. So 25 wants you to make a stab at finding a limit at infinity. First, do the table, and then confirm your limit on your graph. All right, I'm going to jump into the algebra because the video is already getting kind of long. So 27 kind of through 38 wants me to find limits at infinity. I don't need to use my calculator at all. In problem 28, I'm going to multiply everything by 1 over x because x to the first power is the highest power of x that occurs. So I'm going to say 28, the limit as x approaches infinity of, then I'm going to go 3x times 1 over x plus 1 times 1 over x. And then in the denominator, I'm going to go 5x times 1 over x minus 4 times 1 over x. And now I'm going to cancel. In the numerator, this x and that x will cancel. I'll multiply the 3 and the 1 and get a 3. So I'll be left with a limit as x approaches infinity of 3. And then the next piece, I'm just going to multiply the 1 and the 1 and leave the x in the denominator. So 3 plus 1 over x. And the first thing in the denominator here, I'm going to cancel the x's. Fractions are gone. I'm going to multiply the 5 and the 1 and get a 5. Bring down my minus sign. No canceling for the next piece. I multiply the 4 and the 1, get a 4, leave the x in the denominator. Now I can plug the infinities in. When I plug the infinity in, I don't write the word limit anymore. So this is going to be 3 plus 1 over infinity divided by 5 minus 4 over infinity. The pieces that have infinity in the denominator are equal to 0. So this is going to be 3 plus 0 over 5 minus 0. So my answer to problem 28 is the limit's going to be 3/5. If I graphed it on my calculator would get close to the decimal version of 3/5, which is 0.6. All right, hopefully you can make a stab at 27. I'm going to try to get these done without having the video too horribly long. All right, so I'm going to do the same process for 30 as I did for 28. The highest power of x that I see is x squared. I'm going to multiply everything by 1 over x squared. So I only do this strategy when I'm finding a limit at infinity. Limits at non-infinities are usually factoring and cancelings when you have fractions, or plugging the number in. I was writing down the simplified version of this. So I'm going to start off doing this as the limit as x goes to infinity of 3x squared, since x squared is the highest power of x that occurs, times 1 over x squared, and then plus 2x times 1 over x squared minus 5 times 1 over x squared, and then divided by 7x squared times 1 over x squared plus 4x times 1 over x squared minus 2 times 1 over x squared. So I multiplied everything by 1 over x squared because x squared was the highest power of x that occurred anywhere. In the numerator, first I'm going to cancel those x squareds. I'm going to be left with 3 times 1, but no fraction left. I get a 3 first. Second piece, I cancel this x with one of those x's. I'm left with an x to the first in the denominator. That x is gone. I multiply the 2 and the 1. And the middle piece is going to be 2 over x. The last piece, there's no canceling. I just multiply the 5 and the 1, and I get minus 5 over x squared. Move down to the denominator. Cancel the x squared. Fraction's gone. Multiply the 7 times 1 and get a 7. Next piece, 1x cancels from the numerator, cancels with that 2 x's, leaves me with 1x. Multiply the 4 and the 1 and get 4 over x. Last piece, nothing cancels, multiply the minus 2 and the 1 and get minus 2 over x squared. Now I have all the x's in the denominators. I can plug in infinity for the x's. I'm going to get 3 plus 2 over infinity minus 5 over infinity squared over 7 plus 4 over infinity minus 2 over infinity squared. And that's going to be 3 plus 0 minus 0 over 7 plus 0 minus 0. And the answer to this problem is going to be 3 over 7. So the limit as x goes to infinity of that fraction that we had at the beginning is 3/7. So hopefully you could do the same thing for 29. You're going to do the same starting point, multiply everything by 1 over x squared, and the limit should just kind of fall out. To do problems 31 and 32, the highest power of x that occurs is x squared. I'm going to multiply everything by 1 over x squared. So on 32, I do the limit as x goes to infinity. I'm going to go 3x times 1 over x squared plus 1 times 1 over x squared over 5x squared times 1 over x squared minus 4 times 1 over x squared. In the numerator, this x and one of those x's cancel. I'm left with an x in the denominator. I multiply the 3 and the 1, and that first piece is going to be a 3 over x. The second piece, there's no canceling. I multiply the 1 and the 1 and get a 1 over x squared. In the denominator, first canceling, the x squareds cancel completely. The x's are gone. I multiply the 5 and the 1 and get 5. Last piece, nothing cancels. I multiply the 4 and the 1 and get 4 over x squared. Now I'm plug infinity in for the x's. Stop writing the word limit. So I'm going to go 3 over infinity plus 1 over infinity squared divided by 5 minus 4 over infinity squared. All the fractions that have infinity in the denominator are going to be 0. So this is going to be 0 plus 0 over 5 minus 0. And that's 0 over 5. And when we have a fraction with a 0 in the numerator, the limit is 0. If that 0 was in the denominator, the limit wouldn't exist. So anytime I'm doing a limit at infinity and I get a 0, you won't get a 0 over 0 like we did in the non-infinity limits. You'll get 1 0 if you get any zeros. If it's in the numerator, the limit is 0. If it's in the denominator, it is undefined. Alright, so hopefully you could do 31. I'm going to get 34 and 36 done. I might run out of time on the video before 38. And if I do, I'm not going to extend this to a triply long video. So 34, the highest power of x that occurs is x cubed. I multiply everything by 1 over x cubed. So this is going to be the limit as x approaches infinity of 3x squared times 1 over x cubed plus 2x times 1 over x cubed minus 5 times 1 over x cubed divided by 7x cubed times 1 over x cubed plus 4x times 1 over x cubed minus 2 times 1 over x cubed. And now I'm going to cancel. The 2 x's here cancel with 2 of those x's, leave me with 1x. The first thing I'm going to write in the numerator is going to have a 3 when I multiply those over x to the first. The second one, I'm going to have a 2 in the numerator by multiplying those. I'm going to cancel one of those and have an x squared in the denominator, so I'll get plus 2 over x squared. And the last one, I'm just going to get minus 5 over x cubed. Move down to the denominator, cancel the fractions for the first piece. I'm left with 7 times 1, which is 7. Second piece, the x's cancel a little bit. I'm left with an x squared in the denominator and the 4 times 1, which is 4 in the numerator. Last piece, nothing cancels. I multiply the 2 times the 1 and get minus 2 over x cubed. Now I'll plug my infinities in and stop writing the limit sign. So I get 3 over infinity plus 2 over infinity squared minus 5 over infinity cubed for the numerator. The denominator is going to be 7 plus 4 over infinity squared minus 2 over infinity cubed. All the pieces with infinities in the denominator are zeros, so this is going to be 0 plus 0 minus 0 for the numerators over 7 plus 0 minus 0, which is 0 over 7. And when a fraction has a 0 in the numerator, when I'm finding a limit at infinity, the limit is 0. So hopefully you can skip back and do 33. When I get 36 done, hopefully I can get 38. I'm picking up the pace just a little bit because I think the algebra at this point should be easy to follow. And I want to get as many problems as I can in the amount of time the video lets me shoot. 36, I'm going to multiply everything by 1 over x squared because that's the highest power of x that occurs. So I'm going to go the limit as x goes to infinity of 3x squared times 1 over x squared plus 1 times 1 over x squared over 5x times 1 over x squared minus 4 times 1 over x squared. The reason I picked x squared, it's the highest power of x. And now I'm going to cancel and figure out what's left. Here in the numerator, the x squareds cancel. I start off by just multiplying the 3 times the 1, and I'm not going to have a fraction there. The next piece, nothing cancels. I multiply the 1's together, and I get 1 over x squared. And then in the denominator, this x cancels with one of those two x's, leaves me with 1x. I multiply the 5 times 1 and get a 5 in the numerator, and the 1x that's left over in the denominator. Last piece, nothing cancels, so I multiply the 4 times the 1, and I get minus 4 over x squared. Now the x's are stuffed in the denominators. I can plug my infinity in. When I plug my infinity in, I stop writing my limit sign. So I get 3 plus 1 over infinity squared divided by 5 over infinity minus 4 over infinity squared. And that's going to be 3 plus 0 in the numerator and 0 minus 0 in the denominator, which is 3 over 0. And when I'm going to find a limit at infinity, the 0 is in the numerator, the limit is 0. If the 0 is in the denominator, the limit doesn't exist. So I'm going to skip 38. It's going to be another does not exist. It works just like 36, but I'll run out of this video time if I go any further. But I will put 35 up, and that's 37, which you need to do after 35. Both of them are going to be limits that don't exist. All right, so if this video felt a little bit rushed, if that's the case and you can't follow it, tell me that you weren't happy with the video, and I'll re-record it at a little slower pace, and then maybe make it a little bit longer in length. But I'm hoping that it was followable enough, because hopefully your algebra skills are good enough now that you can, if I go a little bit quicker with my algebra, that you can handle it, because that's going to be necessary as we get deeper in the class. The algebra is going to get messier and messier, and I won't be able to go as slow as you might like me to.